Today is March the 22nd, 2015, and this is the Sunday Basement Hangout. The topic we're going to be taking up is going to be based on this paper I wrote about Vernadskian time for humanity. So the theme is basically time, different aspects of time, and in particular, we're going to be looking at what makes human time so unique as a scientific concept. Time is something that exists in the world. It's a concept that we use, and it has developed as a concept just like basically every concept that we've ever used and tried to introduce into our understanding of nature. These terms themselves have changed over time, just as we've introduced new principles, new concepts. The language itself has also developed. So a lot of even the words and the way that Kepler would speak about motion and inertia and momentum, those words don't really have the same meaning that they do today. Space doesn't have the same meaning, etc. So what I want to do is give a bit of setup about why wrote this in the first place, and then give a quick review of the overall basic concepts in the paper. But I don't want to take too long doing that because I want to hear people what people are thinking about on this. So from the top down, we have been, over the course of the past month and a half, exploring two avenues of differentiating the human species from all others and from any other phenomenon that exists in nature. Those two approaches, I think, are reflected in the work of Kepler and of Vernadsky, where Kepler, who Lynn has been emphasizing as the figure to understand, to have an idea of what humanity ought to be, has the great benefit of having gone through in great detail how he made his discoveries, how he thought, etc. Very pedagogical. Living quite a bit after Kepler, although it wasn't only time that made him who he was, but he's able to reflect on the hundreds of years of modern science that have existed at that point, thanks to Kepler. I mean, Vernadsky is this is 3 centuries after Kepler, so there's a lot to look back on. A lot to look back on science, a lot to look back on economics, to be able to look at the human species in terms of what characterizes our behavior as a whole, as a physical force, in a way that wasn't really as available to Kepler. So I think I see those as two different ways of looking at the uniqueness of the human species. From the inside of that discovery process, and from the outside of looking at how that changes the manifestation of our behavior in the universe. So that's sort of what the background was on it, and I thought that we'd been looking usefully at some of the aspects of Vernadskian space, about how the potential that Riemann made in saying, space isn't flat, space isn't geometric, it's physical. And then Einstein gave a specific way that space was shaped based on the physical principle of light and relativity. And Vernadsky was saying, well, how is life going to introduce new concepts into the space, the shape of space? That there could be characteristics of the shape of space that are found uniquely coming from biology. So, we talked about that over a couple of months or whatever, and so I wanted to take up time as the other big issue. So I think that, let me just say the main point, one of the main points in Vernadsky's 1930 paper, and then describe the different kinds of time that I talked about in this paper, and then we can, discuss things. So, Vernadsky, in this 1930 paper, The Study of Life and the New Physics, well, the title tells you, he's talking about how the study of life will give us a new physics. And he's able to reflect back, writing this in 1930, on the changes that just occurred over the short span of a few decades before this paper was written, where there was a new physics created by Planck and by Einstein, where those discoveries of the quantum and the small, relativity and the large on the shape of space on the whole, that those discoveries really redefined everything about physics. Not only the conclusions we would draw about things and studying them, but about the very basic language, the basic concepts that we use to frame our ideas about nature. So Vernadsky says, he says that space, time, matter, and energy are clearly distinguished for the naturalist of the year 1929 from the space, time, matter, and energy of the naturalist of 1900. And briefly on that, Einstein showed that space was not the flat, featureless, unmovable, lacking all characteristics space that Newton believed to exist. That space was curved, and also that space and time, which had been considered as totally separate things, right? Space and time, they don't share anything in common. You don't talk about how many feet it took you to eat your lunch. You talk about how many minutes it took. You don't say, how many miles ago was it that Cusa lived? You don't talk that way. Space and time were separate. And what Einstein showed was that was no longer the case. So with examples of whether two events are at the same time, or if A is before B, or B is before A, or A and B are at the same moment, three different observers moving relative to these events might come to all three of those conclusions. One observer says, oh, A happened, then B. The observer standing here says they're at the same time. The observer moving this way says B happened, then A. None of them is more right than the other. That time no longer exists independent of space or of your position and movement in space. So this is a radical reconception of those two very basic concepts, space-time. Same with matter and energy. Atoms weren't considered by everybody to be a true thing in 1900. By 1929 they were, thanks to the work of, large part to the work of Planck's student von Laue, who had done X-ray imaging of crystals and showed the atomic structure. It wasn't broken up into pieces. Ever since Huygens and the wave theory of light had trounced Newton's idea of particles, for over a century, light was waves. It wasn't particles. But now, thanks to Planck and Einstein and the quantum and the photoelectric effect, energy now came in pieces. Also, energy and matter were no longer distinct. Right? Einstein showed that space and time were no longer independent things. Position in space and time used to be considered as independent. Einstein showed, nope, it's all together. He also showed that energy and matter, which you used to say energy is conserved, matter is conserved. Einstein said, well, not with E equals mc squared, they're not. Now there's a connection between energy and matter, which also used to be separate, and now they're not. But now, thanks to Paul, with that special kind of physical process in the nuclear world, you can actually have energy and matter change into each other. So if Vernadsky is able to look back on those 30 years before he wrote this paper and say that if the words space and time and energy and matter don't even mean the same thing anymore, wow. How is biology possibly going to change our idea of the basis of physics? Vernadsky asks two questions. He says, is this list of basic concepts complete? And second, are the meanings we associate with these terms the final ones and the most correct ones that they could be? So Vernadsky is he's cutting right into the core about how you practice science. He's going beyond conclusions in science, and he's really looking at how you do it, how you discover new things. And so he asked the question, how can biology, how can thought change these things? So that's the setup. So now to go over the different kinds of time I had brought up, and I'd realize, well, also if when you had printed it none of the footnotes showed up, this is a technical thing to say, but you have to download, Google Docs is having a problem. You have to download the Google Doc as an open office file or a Word document and then print it from that program. If you just try to print it, all the footnotes disappear. And there's a lot, and they're almost like boxes. Some of them are kind of long. So, okay, so the kinds of, so the focus of this paper was time. So we're not looking at space, energy, or matter right now. Let's focus at time and how that as a concept can change when we start looking at it as biologists and as economists and as people who intend to change history. So just sort of going back through the history of it as a concept, before the second law of thermodynamics, any physical principle that anyone had ever expressed, although it described, they described rates of things occurring in time, they never distinguished between one direction of time and the other. So for reversible processes, like a planet going around a star, a planet could go around a star in the other direction, and that's not going to, you wouldn't know which way is the right way based on just motion. It doesn't make a difference. If you had a pendulum, let's say you got a pendulum swinging back and forth. And according to the conservation of energy, which really first came from Leibniz, there's either, Leibniz would say that the pendulum at its top has vis mortua, dead force. It's ready to fall down. And as it's falling and it's down at the base, it's going as fast as it can. It has no more vis mortua, no more dead force, because it's fallen as far as it can go. And now the motion is living. It's vis viva. Today, that's called potential energy, based on the height, and kinetic energy, based on the speed. And as that pendulum goes back and forth, the energy is either potential, or it's as fully actualized as it can be, or it's somewhere in the middle. If you stop that pendulum at a moment and look at it, do a freeze frame, and you say, I know where this is, and I know how quickly it's moving. You could say where it will go in the next moments. You could write formulas and solve them, and you'd get your equation for how the pendulum would move. You could also, if you took a freeze frame at that moment, go back in time and say, what had it done before that moment? And you could make your formulas go backwards in time. They'll all work just the same either way. You can't, nothing in the way that they're written, nothing about any of these formulas, nothing about any of these principles distinguishes one direction in time from another. That was the understanding of things. The development of thermodynamics had to take into account, one of the things it took into account was the fact that not all processes can go either direction. For example, you can turn motion into heat pretty easy. Just, rub your arm like this and you'll feel it, you just made some heat. Your arm got hot. If you, put a hot piece of, if you put a warm washcloth on your arm, put your hand on it, it's not going to make your hand start moving back and forth, right? The heat isn't going to start pushing your hand. So that's one where it's, it doesn't go either way. Hot surfaces don't make things move along them, but things moving along surfaces heat them up. That's an irreversible process. Or if you had a can of compressed air and you knock the valve on the top off of it, all the air is going to spray out of the can into the room. You never see that go the other way. You never have it where you open up a can and then all of the air in the room gets sucked into the can and everybody, suffocates. That never happens. The other direction does happen. And it was very confusing because nobody really had any explanation of why it would go this, why it could only go this, why it can only go this one way and not another. So what got introduced was this concept of entropy, which, at first did not have all the implications of the universe is going to end in heat death, and entropy always increases universally and everything in the way that some people say it today. But it was introduced as a concept. It was something that you could measure about a gas or about a system. You say, like, take the volume and the temperature and the pressure, etc. You can calculate the entropy, and there was no process where the entropy would decrease. There's no process where the only change would be the entropy decreasing. Right. So when that gas expands, for example, the amount of energy in that gas, according to the thermodynamics, didn't change. The energy didn't change, but the entropy did get bigger. So this now gave an arrow to time, a direction to time. Any process where the entropy changes, now people would say, well, forward in time is where the entropy got bigger, and backward in time is where the entropy got less. So now there's a distinct way of saying forward in time versus backward in time, as opposed to only saying opposite. Remember when we talked about, I don't know, a month or 2 months ago about left and right, about left and right-handed molecules? You really can't say anything about them besides the fact that they're opposite. And, you know, some of us have tried doing these experiments of, you know, if you were speaking to an alien civilization and trying to describe to them, you know, over the telephone that your heart was on the left side of your body and not your right, and most people are right-handed, you'd have a very hard time trying to explain that to them, because although up and down, you could say, you know, things fall down and up's the opposite direction. You know, forward is where your eyes are facing and backward is the other way. Left and right, they're opposite, but is there anything unique that you could say affirmatively about one versus the other to actually describe them separately? And that had been the question since Pasteur and Curie, and then Vernadskian was looking at why is it that, I might get it backwards, amino acids are left-handed, carbohydrates are right-handed. Why is that? Is there something inherent about it? Etc. With time, it's not such a dilemma. With time, we definitely have a way of saying what makes forward in time different from backward in time, and entropy provides a way of saying what that direction is. You know, then I went through in the paper why, you know, it's, you know, talking about rooms getting messy and things like that has nothing to do with entropy. Entropy is about it's a law of thermodynamics. It's about like gases and chemicals reacting with each other. It's not about society. It's not about social structures. It's not. It just has nothing to do with that at all. That would be like saying that trying to apply gravity to, you know, music or something. It just doesn't make, you know. You say music, you know, heavier music falls quicker than, it doesn't make any sense, right? It's just a stupid thing.
That's what Kepler did. Just kidding, though. Just kidding.
What's that?
That's what Kepler did, but I was just kidding.
Huh? Oh.
Apply gravity to music.
Oh, yeah, right, yeah. Anyway, so, okay, so we got this sort of direction. That's something. That's still in physics. That was around at Vernadskian's time. But now let's take a look at things that are especially biological about time. One thing is that time becomes quantized again. Time becomes quantized when you're looking at biology in a funny way where, okay, it has a character of being quantized and it has a character of having only a local meaning. So just like Einstein would say before, after, simultaneous, depends on who is observing it, the quantum nature of time, unlike for energy, depends on the space in which that time is existing. By that I mean it depends on which organism's time you're describing. So generational time, that's indisputably a very clear empirical generalization. Generations exist. You know, that's part of life. That's definitely something that exists about biology. You know, as Ben had been pulling up some research on this about how there's, roughly speaking, scaling laws about how, you know, bigger mammals have longer lifespans, smaller mammals have shorter lifespans, and, you know, based on the mass, you can predict somewhat accurately, in a general way, what the lifespan of an animal would be, or its time to double its population, or its gestation period for placental mammals. So you got this definite quantized nature about time in biology that depends on the space of the organism in which that time is unfolding. That's something new, quantized time. Another thing is that you have got a kind of time where before and after aren't distinguished by a number that got simply bigger or smaller, entropy. Any future time, you might just say, well, the entropy just got bigger into the future. Take what entropy we had in the past, it got bigger, and then, you know, in the future, that would be describing the future. In evolutionary time, that's just not the case. And so with these biogeochemical principles of Vernadskian, that over evolutionary time, organisms make use of a greater supply of energy, that the biogenic flow of material and energy increases. That over evolutionary time, it's those species which participate in that overall increasing energeticness of the biosphere, those are the ones that continue to exist over evolutionary time. So those changes aren't always smooth. The development of photosynthesis, that's not a minor tweak. Right? The development of photosynthesis, so now let me bring in economy too. Okay, I recognize I'm sort of, that was on a track, and I'm just going to leave it now. And I acknowledge that I'm doing that. Let's take a step back and look at how we'll end up revisiting that. But let's just go straight to humanity. And let's look at how human economy shows that the first and the second laws of thermodynamics are untrue. The first law of thermodynamics says that the amount of energy is constant. That pendulum, when it's up here, it's got potential energy. When it's at the bottom, it's got plenty of kinetic energy. But overall, as this pendulum moves, the total amount of energy, potential plus kinetic, doesn't change at all during that motion. So that's the principle of that's the first law of thermodynamics. For humanity, that is not true. When this was first considered and really formulated as the laws of thermodynamics in the 1800s, nobody knew about nuclear processes. If you tried to say all the energy in the universe, you wouldn't include uranium, you wouldn't include thorium, you wouldn't include deuterium, you wouldn't include antimatter. And that was why Thomson was, over an order of magnitude wrong about how old the sun was, because he assumed it was based on chemical principles, and that's just what people knew of. So you might ask the question, after Einstein and E equals mc squared, first off, the conservation of energy is no longer true. We can now turn mass into energy. That's what nuclear processes do. But the other thing is, you could ask, did we just discover that there was more energy out there, or did we create more energy? And an atom would answer, you found the already existing energy. Except atoms can't talk. So we're not going to care what they say. A person, an economist, would truthfully and most rigorously say, we increased it, we made energy. Because, remember, we're a force of nature. When we're trying to talk about physics and science, we shouldn't pretend people don't exist when we're doing that, as though we're watching and looking at a world that we don't exist in, don't live in, don't act on, don't shape. We do all of those things. We're a force of nature, and the energy available to the forces of nature to cause things to occur, the power of overall possibilities in nature, including us, increased. We created more power. So that's one thing. So the first law of thermodynamics does not apply to human beings. We create resources, not just physical ones, energetic ones as well. We make petroleum a resource instead of just a mess by being able to use it to do something. The second aspect is the second law of thermodynamics, which I presume almost everybody's probably heard, the idea that the universe will eventually, as entropy becomes as great as it could ever be, energy will be unavailable to do any work. The kind of energy that's least available to do work is when everything is just hot. If you made everything hotter, the energy would have been, that's more energy, but it becomes less and less useful. If you tried to drive a car in an atmosphere where it was already 1,000 degrees, for example, this is a silly, but it's true. You're driving your car and the weather was 1,000 degrees outside, and you better hope your air conditioner works. Yeah, right. So you're driving around. Your car is going to be way less effective, because if the air in that cylinder is already that hot, then when you have the combustion of the fuel and it got hotter to push the to push the piston down, that's what drives a car. It's going to be less effective because it was already so hot, and the addition of heat is going to push the piston less. I brought that up just to give some sort of specificity to the idea of why, when everything's warm, you lose your ability to do things. That's also not a universal principle at all. We've created this kind of energy. And then the other aspect of it is this concept of energy flux density of LaRouche's. And so I gave an example in there of a heat pump. I recognize not everybody, they don't have them everywhere in the country. You might have never seen one of them, or maybe know how they work. But and it also might seem like it's not the most profound example ever. The reason I chose it was because it's actually such a low-level effect of the technology. Here's the point that I was making in the paper. I said, if you take natural gas and you heat it, I mean, you burn it. You've got a natural gas furnace at home. You're using it to heat your house. A good furnace will take 90% of that heat from the natural gas and actually warm the air in your house with it. That's pretty high efficiency. If you took the natural gas, burned it in a power plant, you're only going to get 42% of that gas's potential energy, of the heat in the natural gas. Only 42% of it comes out of the power plant on the power lines. 58% of it's lost. It's gone. You're not going to do anything with it. It just made the air hot. It came out of the exhaust, the chimney or whatever. Useless. Didn't do anything with it. Just made it a little bit warmer outside, which might be nice in the winter, but you'd hardly notice it. But then you could take that 42% of that electricity, because electricity is a much higher energy flux density than just heat. Well, like in the Gifts of Prometheus report, we had those stages of energy, the different kinds of fire. What can you do with a wood fire? You can heat things. What can you do with electricity? You can do a lot of. You can have lasers. You can talk to people. You can have phones. You can have robots assembling things in factories. It's phenomenal what you can do. And you can use your electricity to heat. And it's way better than using wood to do it, because basically the way a heat pump's an air conditioner in reverse. What it does is it takes heat from outside. Like even when it's cold outside, the air could have been colder. So the heat pump takes heat from the air outside your house and puts it in your house. And the efficiency it's certainly over 100%. It's 200 or 400%. However much energy you put into your heat pump, you get several times that amount of heat delivered into your home to keep you warm. So even if you lose more than half the energy in that natural gas, turning it into electricity, even for providing the most basic type of power of just heat, even then you get more heat by turning the gas into electricity and using it in a process that simple heat couldn't do, running a heat pump. So this curious feature of technology, LaRouche refers to how two machines, one is able to do more even with less. One is able to do more than the other machine, even if the other machine had the full amount of energy. That's an example of that, an energy flux density. So those different kinds of, the other different kind of time that we get here is that, entropy, I left out the statistical, we can bring it up in the discussion period, but the statistical idea of thermodynamics says that increasing entropy really comes down to finding things move towards states that have more ways of being, that are more, you might say, more likely, more possible, more probable. Those aren't quite exactly right, but that's the main gist of it. That when you opened up that can of gas, there's a lot of ways for gas to be all over the place in the room and in the can. There's many fewer ways for all those particles to be in the can. So even if you open the can, all the air, the gas comes out. If you played that video in reverse, it wouldn't violate any of the laws of physics. It would all go back into the can. That's fine. But there are very few cases of starting with a room full of gas where they'd all be moving in just the right way to end up going into the can. The difference is that what we do, what life does on an evolutionary scale, is move towards things not that are more probable, not towards things that are simply less probable either, but towards things that are not possible. So the future that we create with the principle of the flank, with economy, with creativity, the future that we create isn't one that was very unlikely to exist. It's one that the past itself could never have led to. And the creation of that different future we find in the very special type of now that exists for us. There's no now in physics. Right? You'd be hard-pressed to define now without using human beings. I mean, just trying to, unless you're able to say, oh, the moment we're thinking about things right now. That's our now. The fact that it's now is that we're able to think about it right now, and mentally we've got a difference between the future, which is undetermined, the past, which already happened, and our chance right now to decide what we're going to do. Free will makes the now. In physics, the future, the past, they're both equally known. That's an important one. They're both equally known. We're that pendulum. All of the physical laws, the tools that we use. I'm not saying nature actually operates this way, or the galaxies don't evolve. What I'm saying is our understanding of it and the things that we've codified as discoveries about it, the pendulum going forward or back in time, indifferent. The Big Bang, a long time ago, that just comes from saying, how do things happen right now? Let's take them back. The heat death of the universe in the future, that's just saying, let's take what's happening right now and move it forward. They're about equally well known, and they're not known. But okay, so this now that exists only for people, and remember from this Einstein thing about how different observers see events as being simultaneous or before or after each other, human beings don't even have the same now. I mean, there's no way to separate now from that. There's no time without a place in space and emotion in space. There's no now except for which person's now is it. What will you do? That's the substance of time, is that will you do something to create a future that couldn't have existed from what the past is? And the opportunity to do that, that's what makes us human. The goal of economy, the goal of statecraft is to get as many people as possible in an increasing way participating in that process, leaving these contributions that take the shape of creating it such that, the time now or the future is one that couldn't have been reached from the past. And that, after you think about all of this stuff, it becomes totally silly to try to say, well, yeah, but let's start with physics. Let's go back to the idea of time from the atomic clock, and let's see if your theory fits with that. Why bother doing that? And so I think Vernadskian really is great at freeing us from the unnecessary obligation of even trying to explain everything in terms of particles and physics and all that kind of thing, when you can simply say, what can we actually discover about biology? What can we actually discover about human beings? And then go backwards. That redefines time. So, as the title of Vernadski's paper said, that would be, that's how the study of life is going to give us a new physics. Or if you look at, the work LaRouche has done, how does economy give us a new physics, a new biology? As you get these like energy flux density, potential relative population density, those are discoveries that both help understand what economy has been, and by using them as discovered principles, can allow us to better plan for the future and create an even better future than would be possible without them, which makes them economic discoveries. So that's what I wanted to say. That's the opening.